Well, good evening, everyone, and welcome to the June edition of 60 Minutes in Space. I'm Steve Lee, the Curator of Planetary Sciences here at the museum, and I want to welcome all of you on this hot, smoky summer evening. And tonight we're going to depart from our usual format. We've got a special guest lecturer, Dr. Don Hassler. He's the Principal Investigator on the Radiation Detector experiment, which has been flying on the Mars Science Laboratory. And well, he'll tell you what it does. I don't want to get into that, but it's the only instrument that has actually been collecting data since launch. And Don is, let's see, a graduate of CU Boulder. 1990, he received his PhD, and he's been working for Southwest Research Institute in Boulder since 1997. Okay, and you know, it's always nice to see the local involvement in missions like this. And of course, Denver, I think, is sort of Mars Central. Lockheed Martin has built many of the spacecraft that have gone to Mars. They have a major role in MSL. United Launch Alliance builds the rockets that get them there. Lots of other companies in the area contribute to this, and then we have the research community as well. So I think without further ado, I'll turn it over to Don, and we'll stick with our usual format. If you can hold your questions to the end, we'll have plenty of time for question and answer. When Don is done, I'd like to just make a few announcements, and then we'll open it up to Q&A. So please welcome Don Hassler.
Thank you, Steve. And thank you all for coming. It has been a smoky few days. In fact, just as I was leaving to come here to the museum, there were those lightning strikes in my neighborhood, starting a couple of spot fires, but it looks like they're under control now. So anyway, I'm going to talk to you this evening about the Mars Science Laboratory and one of the 10 instruments on the Mars Science Laboratory called RAD, which is going to be used to help plan for future human exploration of Mars one of these days. So the Curiosity, which is the name for the rover that was selected through a competition, is the largest sibling of the NASA rover family. It's about the size of a Mini Cooper. It's the next generation up from the two Mir rovers, Spirit and Opportunity, and it really is an order of magnitude more capable in terms of its science capability as well. Here's another side view of the size, but it's at least it's over 10 times heavier than Curiosity, and much more capable. Curiosity had about 4 instruments on it, and MSL has 10. So this is a view of what it looks like with people in the background. Here's some of the people working in the clean room with Curiosity just before it's getting ready to be integrated with the spacecraft and the aeroshell. This is kind of a schematic of what that looks like. It basically is in this clamshell. It almost looks like the crew exploration vehicle, which will send humans in down the road, which is one of the themes of my talk coming up in a little while. But this is the rover itself, and then it has a descent stage. I'm going to show a movie at the end which shows the little discussion of the 7 minutes of the entry, descent, and landing process for the Mars Science Laboratory, which promises to be extremely exciting, and then all the other necessary spacecraft components to get it to Mars in one piece. This is what it looks like in hardware. It's actually really still quite large. These are full-size people next to the full-size spacecraft, and then it was launched down in Florida at Kennedy Space Center on, let's see, what was it? It was Saturday, the 26th of November, 2 days after Thanksgiving. It was originally scheduled for the day after Thanksgiving, and that slipped a day. So here's a view of the launch. There's actually some URL links to the launch on the web that you can look at. It was launched on an Atlas V rocket, which is one of the largest rockets that we can send spacecraft to other planets. It had a Centaur upper stage, which gave it a kick boost on its way to Mars. So about a couple of hours after it was launched, it went about halfway around the Earth, and then on its way to Mars. And it's about an 8 to 9 month journey from Earth to Mars. And my instrument was turned on 10 days after launch on December 6th, so we've been operating now for over 6 months. I'll talk about that in a little bit. The landing site, the destination we're going to is a site here. It's called Gale Crater. This is the location of the other rovers or other landers that we have. Some of those are rovers, some of those are just landers. But the Spirit and Opportunity, those are the two rovers. They were in these two locations. Curiosity, in a not too different way, is also in a crater. It's going to land in an impact crater called Gale Crater. It's quite interesting because it's this large crater. This ellipse is 10 kilometers across, or about 6 miles across. I think Steve has a slide. There's a more recent slide that this ellipse now has actually shrunk a little bit. We have a little bit more confidence in our pointing and our landing avionics, so we're actually going to be able to have a more accurate landing here, get to land a little bit closer to the central mountain here. This mountain is about 3 kilometers high, or not quite 2 miles high, and it basically has sedimentary rock all along the sides of it, both on the inside and the outside. So that'll tell us, it'll help us look back into time to see what Mars was like, or what the geology of Mars was like, millions of years ago. So the primary objectives of the Mars Science Laboratory, in the past, the MER rovers were looking for water. MSL, or Curiosity, is looking for signs of habitability, meaning the ability to sustain life, or limiting factors to sustaining life. So we want to not just look for signs of current habitability, which you could argue if that's how likely that may or may not be, but also past habitability. When Mars had a thicker atmosphere, a thicker climate, is it possible that there might have been microbial life back then? These are all very interesting and open questions. So not only will we be looking for water, but also carbon-based rocks and minerals in the regolith, but then also looking for life-limiting factors, things which would make it difficult for life to evolve or to survive. And radiation is one of them, and that's why we're flying my instrument, the Radiation Assessment Detector, because it's going to look for these life-limiting factors for life. So here's a cartoon of the rover with locations of the 10 instruments with little arrows for them. I'll talk about each instrument in a moment, so we don't need to go into detail here. Our instruments here, this is the power supply for the rover, the power source, and then this arm right here is about a 7-foot long arm, which can reach out and sample rocks and bring them back and stick them into sample containers on the rover. So all in all, there's about 17 cameras. There's a really exciting laser to zap rocks and look at the evaporation from the rocks, drill to collect samples, and then the radiation detector to measure the radiation environment. The eyes of the camera are here on the top of this mast, thus the name Mastcam. And this will help us not only do, actually James Cameron is a co-investigator on this experiment, and so the expectation is that we will be able to produce three-dimensional views, three-dimensional movies actually, as MSL rolls along. The data volume is not real great, so it's going to take a little bit of time to send all that high-def video back, but we promise to have some of the best images and video of the surface of Mars and of what we're trying, the science that we're trying to do of any mission to date. This is the instrument as well as the laser head for the laser zapping, or the rock zapping, the laser zapping rock. No, the rock zapping laser. That's it. A little dyslexic, but I'm still recovering from the fire near my house. So in the next to these Mastcam cameras is the laser that actually points out, and then there's a little spectrometer, which is basically an instrument that splits up light into colors with a little telescope on it, and it's going to look at the rock where the laser hits, and it's going to look at the evaporation from that rock and try to identify what the elements, or what the rock is composed of for rocks that we actually can't reach with the arm. So that's a very interesting rock. Here's kind of an animation of what that's going to look like. So this instrument's actually really captured the attention of a lot of people. You'll probably hear more about it as we get closer to the landing date on August 5th. We also have a weather station called REMS, which is actually being contributed by the Spanish. MSL is an international mission. The French are actually contributing to ChemCam, the laser. The Spanish are actually contributing this weather station. So we're going to get daily weather updates from the surface of Mars. There's actually quite a bit of wind there, and the temperature and the humidity go up actually quite a lot. If we think the temperature varies a lot in Boulder, temperature varies even more on the surface of Mars. It can go up by 100 degrees in a day. And Boulder and Denver, it maybe only goes up 40 or 50 or 60 degrees in a day. So that's nothing compared to Mars. There's also this long arm, which has basically its hand at the end. This hand actually is a series of different scoops and drills and all sorts of different types of instruments to be able to sample the rock. And this will reach out and then feed the entrance to three different instruments on the interior and the inside of the rover itself. Each of these is a rock analyzer. So we have one instrument which is actually a Canadian contribution to identify the chemical elements in the rocks or in the regolith. And then there's an instrument which is from Ames Research Center to identify the minerals that are actually formed which are frequently formed in water. So if you find these minerals, you know that they have a history of having been evolved and formed in water, and that tends to be leading to the possibility for detecting life down the road. And then SAM, which is it looks like a big box, but it's actually a very complex analytic lab. It's like a chemistry analytic lab that one might have at the university to look for signs, look for organics or the chemical building blocks of life. This is a very exciting instrument because if we find any signs of organics, that would be, well, Viking looked for these and came up with ambiguous results. Not that we really, it's not clear if one would expect to see these or not. It's been a long time since Mars had a thick enough atmosphere to have quite a bit of geology and hydrology going on. But we want to look back into the past and see if these things may have happened or not. So there's one other instrument on that hand at the end of that arm called MALI, which is basically it's like a magnifying glass imager to basically look at the grains. Basically, we're going to be sampling these very small grains. And so this hand lens imager, if you're a geologist, you know that you use your magnifying glass all the time to be able to get a close-up look at what the structure is of these rocks. We're going to be able to do this in the same way that a geologist would. So a lot of people refer to MSL or Curiosity as a field geologist, with all the capability of a human geologist, and we hope as much smarts. And then there's the last two instruments, last but not least, but I'm leaving them to last because this is the one instrument that I'm responsible for. We have two radiation detectors on the mission. One is called RAD, the Radiation Assessment Detector, and it's actually funded by the human exploration side of NASA to help us plan for future exploration, future missions when we send humans into deep space. And then the other one actually is a Russian contribution to help us identify signs of potential water in either the minerals or in the soil below the rover as we rove around on the surface. This instrument can operate in a passive mode, so it produces results which would be complementary to RAD, but fundamentally it's looking for potential signs of water on the surface. So let me talk a little bit more about RAD because this is, in my opinion, I think this is it's a little bit off to the side of the primary objectives of the mission. The mission is to look for signs of habitability. RAD is an instrument to look for limiting factors for habitability. So, in fact, it really fits into the primary objectives, but it's not a geology experiment. So the geologists would potentially overlook it. But it's actually a very important instrument for understanding if life could have ever existed on the surface. Because if the radiation environment is too strong, either life as we know it couldn't exist that way, or it had to be buried deep below the surface, below the regolith. And so one thing we'll do is by measuring the radiation environment, we'll be able to say how deep would life have to have been below the surface of Mars for life to have evolved. That's very exciting. But then also it'll tell us what the radiation environment will be like or is like now, so that in 20, 30 years, or whenever we send humans to Mars, and it may not even be NASA, it may, Elon Musk from SpaceX, actually one of his top 4 goals in life is to send the first human mission to Mars before any government on the planet. So, you know, he's got great plans with his company, and he's been doing great things. And one of his greatest ambitions would be to have a private manned mission to Mars. So hopefully this will happen. This very well may happen in our lifetime, and RAD will be making measurements to give us precursor measurements to let us know what the environment will be like, so that astronauts know what to expect. The other thing about RAD is we're taking measurements during cruise. I mentioned they turned us on December 6th, so it's been a little over 6 months ago. Initially, we thought that we would do this as a calibration, to get intercalibration with other spacecraft that are up in space and compare our measurements with them. But we actually, in the last year, thinking more and more about it, we realized that it's actually a really good proxy for a human inside their own spacecraft on the way to Mars. So the radiation environment that we're measuring right now in cruise is very similar to what the radiation environment would be for an astronaut on their way to Mars in the future. So why measure the radiation environment? What's the big deal about radiation? Well, radiation really is everywhere. We live in a bath of radiation, different kinds of radiation, of course. The radiation everyone thinks about is chest X-rays. Smoke detectors, you may know, have little bits of a little radiation source to help them detect smoke. One that you may not know is that bananas, the potassium in bananas has a little bit of radiation. So actually, if you, I think eating about 300 bananas is about the equivalent of one chest X-ray. So I love bananas. I'm not worried about it. But the point is that there's radiation in everyday life. And it's across the whole spectrum, from the ultraviolet, which we get when we get suntan or sunburned, to space radiation, which is what you get when you go out into deep space. And so that's the next question, is what is space radiation? What is the big deal about radiation in space? Well, space radiation is one of the top 5 problems that NASA has identified that needs to be understood before we can send humans to Mars. You know, others would be dealing with the dust on the surface of Mars. Others would be life support and the propulsion, things like this. But radiation is actually up there on the top of that list. And there's 2 primary kinds of radiation in space. One is called galactic cosmic rays, and these come from supernova remnants far off in the galaxy. The other kind comes from the sun, or solar energetic particles, and these come from solar flares or coronal mass ejections when the sun erupts in these violent storms. And you may have seen in the news in the last couple of months images of these giant flares that have been happening. The solar cycle is picking back up, the sun is becoming more active, and we've actually had 3 or 4 large flares in the last few months, which RAD has detected inside MSL. But this is the type of radiation coming from the sun. Why is space radiation harmful? Well, it's really high energy radiation. It doesn't have the benefit of the Earth's atmosphere to protect us, or the Earth's magnetic field. It can affect DNA. It can actually alter the DNA, which then leads to cancer. So actually the most prominent risk of radiation in space for astronauts is the cancer risk. Another one would be glaucoma and problems with different forms of eye disease. So we need to understand this. The short-term effects, okay, you might survive, a few years after you arrive back, but if the radiation causes cancer and you die 10 years after you get back, that's still not acceptable to NASA and to us as a society. So why is the radiation different on Mars? Why do we actually need to measure it on Mars? Why can't we just measure it in space or on Earth? Well, the Earth has a magnetic field called the magnetosphere, which protects us. Most of the radiation is charged particle radiation, so it gets repelled from the Earth's magnetic field. A charged particle hits the magnetic field and it bounces off. So that's one. Mars doesn't have a significant magnetic field. We think it may have in the past, but then its liquid core cooled down and it became solid and it lost its magnetic field. It has little remnants of magnetic fields, but it doesn't have a global magnetic field. That's one. And the other is that the Mars atmosphere is about 1% the thickness of the Earth's atmosphere. So it doesn't have the shielding thickness of what the atmosphere, the Earth's atmosphere actually absorbs some of the particles and breaks them up and provides some element of shielding for the particles that actually get through the magnetic field. So the combination of the thinner atmosphere and the lack of magnetic field make the radiation environment on Mars fundamentally different. And so, well, why can't we model this? Well, we do model this, and we think we know what the radiation environment is going to be, but we have to measure it. If we really want to be sure, we need to go and validate the models. We need to make sure that the models are correct. So I mentioned galactic cosmic rays as one of the types of space radiation. They vary, it varies with the solar cycle. So here's an ultraviolet image of the sun at solar maximum. We're going to reach solar maximum sometime next year, 2013. Roughly, although we had a very long extended solar minimum, which is a little bit curious. We don't really fully understand why the sun goes through its cycles, but it tends to go on a roughly an 11-year solar cycle, although sometimes it's 12, sometimes it's even longer. But as the sunspot cycle goes up, the cosmic radiation goes down. The expansion of the sun's atmosphere actually acts as a shield for the cosmic radiation. So at solar minimum, we have the higher levels of cosmic radiation, and then at solar maximum, we have minimum in galactic cosmic radiation. So this kind of radiation varies slowly over the solar cycle, and so sometimes may seem to be relatively constant, but isn't. And then the solar energetic particles are these giant storms. You saw probably on the television, on the news, an ultraviolet image, like I showed earlier, of an erupting event. But this is a side view of what that erupting event would be. This is called a coronal mass ejection. It's a big, huge storm which flies through the solar system. There's been 4 of these since January, and as RAD has measured each one of them along with the other spacecraft, instruments on other spacecraft that have been out there. So what makes RAD unique? Well, landing on another planet requires all the instruments to be miniaturized. Mass is a real constraint. You can't just put huge, massive instruments up on a rocket and send them all the way to Mars. It costs a lot. It's very heavy. We already have to use the biggest rockets we have. So RAD, what makes RAD unique is it's a combination of both a charged particle detector and a neutral particle detector all in one, with sophisticated electronics to process those data, make sense of them, and send them down to Earth with also a very low telemetry constraint. We have mass constraints on a Mars mission, we have power constraints on a Mars mission, and we have telemetry constraints on a Mars mission. So RAD is about a factor of 10 lighter than other instruments that do the same task from a science point of view. It also uses lower power, and it's actually completely autonomous. It can turn itself on, take data, store that data, turn itself off, and do this every hour throughout the mission, and then send it down to the Earth or send it to the spacecraft to be sent down to Earth when it's convenient. This plot here really just shows the different particle types that RAD observes. RAD observes protons, which is charged particles, up through iron, with charged about 26 times the mass of a proton. So basically, the whole spectrum of charged particles that we get in space or from the sun or from galactic cosmic rays, RAD measures. And it measures them in the energy ranges which are relevant towards impact on life and on humans. But it also measures neutral radiation, neutrons. We don't have too much experience with neutrons here, only because, well, I guess certain nuclear reactors would have a neutron environment near the core. But in general, most of the type of radiation we experience here on Earth that you'd have contact with would be either gamma rays or positrons, but not neutrons so much, and then sometimes the charged particles. But basically, these are all the different particle types that one would experience or have an impact on life on the surface of Mars. This is a cross-section of RAD, 3D CAD model of it. These are the electronics boards, and then these are the 2 channels. This is a schematic or a cartoon I'm going to show on the next slide, kind of how this works. But it has this charged particle telescope here, which is about a 65-degree solid angle where we get charged particles coming through and hitting 2 or 3 of these solid-state detectors, either A, B, or C, and then going into these scintillators down here. This is the charged particle channel, and then the neutral particle channel is basically these 2 scintillators, with this is cesium iodide and then a plastic scintillator, and they measure neutrons or other neutral particles like gamma rays coming in from the side, with this anti-coincidence shield. And hopefully that'll become a little bit more clear here. Okay, good, the sound works. This is a cartoon of how the charged particle detector works. So the green particle here is detected by each of these detectors. Each of these, A, B, C, D, E, are all different detectors. For the charged particle detector to work, it has to go through 2 of these 3 solid-state detectors. So A, B, C, boom. It's gotten all 3, it's a valid event. A, B, C, okay, it's a valid event. It gets detected, it deposits energy in each of these detectors. If it comes in at an angle greater than 65 degrees, it only goes through 1 detector. It doesn't go through a second detector. It's not considered a valid event. We can't analyze the energy of that particle if it only goes through just 1 detector. So it needs to go through at least 2, and ideally 3, 4, 5 of these different detectors to be able to process and analyze the results, the energy deposit, so we can determine what that energy is of that particular detector. So that's how the charged particle channel works. The neutral particle channel works in a slightly different way. So this is a charged particle like the one before, a green one. And we call this an anti-coincidence shield. So the blue is a neutral particle. Blue is a neutron, or gamma ray in this case. And the purple is a neutron. So this shield right here detects these charged particles, the green particles. So if a green particle comes, it hits this outer shield and it vetoes the event, so it's not valid. We're trying to discriminate the charged particles from the neutral particles. But when you get a neutral particle, like the blue one, which is a gamma ray, or like the green one, which is a neutron, it goes right through this shield and into these scintillators, and these scintillators accept the energy or record the amount of energy deposited from those 2 different particle types. So in this way, we can measure both neutral particles, whether they be neutrons or gamma rays, as well as charged particles, whether they be protons, helium, or even iron, really heavy iron particles, all with one instrument that really only weighs about 3 pounds and is about the size of a coffee can. Although my girlfriend told me the other day, she said, people don't use coffee cans anymore. They get them in their little Starbucks bag or something like this. So maybe it's the size of a microwave oven. That's something I think we still use these days. But that's how RAD works. And RAD sits basically in the top of the rover with the charged particle channel facing up. So you get these charged particles coming down from space, and it goes in through the top of the rover and detected in our instrument here. I mentioned earlier that RAD is completely autonomous. That means that we can we have a little processor on board that can let us turn ourselves on, configure ourselves, take data, and then turn ourselves off, store the data, and then turn ourselves off and go to sleep into a low power mode. I mentioned that power was one of the constraints of a Mars mission. So we don't have enough power to operate continuously on the Martian surface, but we want to get measurements every hour because we want to be able to characterize the radiation environment as a function of time. So by being able to turn ourselves on, take data, and then turn ourselves off and go into a lower power mode, we can take data every hour for several weeks, actually, before we have to communicate with the rover and send the data back down to Earth. But this makes RAD highly capable because we can operate completely autonomously from the other instruments. We can just do our own thing while they're going off and sampling rocks or whatever it is they choose to do. So I also mentioned that we're measuring the radiation environment in space. Here's a picture of the MSL spacecraft, and here's a picture of the NASA crew exploration vehicle called Orion, which is currently being designed. So when we do start to send astronauts back into deep space, whether they go to the moon or the asteroids or eventually to Mars, this is the type of capsule that they'll be riding in, at least for the moon or asteroid type missions. And surprisingly, it's about the same size and looks a lot like the aeroshell and the spacecraft of the Mars Science Laboratory. So when we're buried deep inside here, we're actually making measurements and observing what the radiation environment would be like inside here, which is very similar to what the radiation environment would be like inside the crew exploration vehicle. So NASA is very interested in our measurements and our observations that we're taking during cruise. And we've been taking 6 months of data now. So I mentioned those giant solar particle events that that we've seen since January. Here's the rad dose data as a function of time since launch. So 6 months is about 180 days. This is starting on December 6th. And each one of these peaks is actually one of those giant solar particle events from the sun that are occurring. And so one of the things we're doing is we're integrating what this total dose would be for each one of these events, looking at the energy spectra from these events, comparing them to other spacecraft. But what's interesting is if you take this dose rate and integrate it over that event and compare it to NASA's lifetime limits for exposure for astronauts in deep space, it'll be a very important and interesting measurement of how close we come to reaching a lifetime limit for what an astronaut should or is able to or allowed to experience in deep space. So the Mars Science Laboratory has been taking observations and doing science throughout its cruise with RAD, even before we land on Mars. And we land on Mars 11:31 Denver time on August 5th. And so I have a video coming up, which is actually a fantastic video. It was just released last week. And this talks about the landing.
Is the result of reasoned engineering thought. But it still looks great. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive. And then, on the surface, for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself. We have a help program. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag, our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constraint space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the realm to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, we undo something, we're just smack right back into the parachute. So the first thing we do is make this really radical endeavor, fly off to the sun.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of the crater, right beside a 6-kilometer high level.
get those rocket engines too close to the ground. Because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud would then go and land on the rover. It would damage mechanisms and it would damage instruments. So the way we solve that problem is by using the Skycrane.
20 meters above the surface. We have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wings, on the surface.
As the rover touches down, it is now on the ground. In the same state, it's in a collision course with the rover. You must cut the bridle immediately and fly to the same stage to a safe distance from the rover.
Thank you. Thank you very much. There's a lot of great websites out there. You can just Google either Mars Science Laboratory or if you're just interested more about RAD, you can Google RAD. You can find other movies like that. But that was released last week, and it's particularly compelling, I think. But anyway. Thank you very much. Yeah. You want this?
Well, thank you, Don. And I've got just a couple of things, and then we'll get Don back up, and I'm sure you have lots of questions. And so we have a couple of events coming up in the next month, the biggest of which is going to be on August 5th. But before that, on July 13th, we're premiering a new 3D IMAX movie called Space Junk. And I'd like to give you just a very brief trailer of this movie.
From the discoveries of space exploration to satellite communication, humans have developed a profound connection to space. Our planet's need for communication has transformed what was once called the final frontier into something far less romantic. We're now faced with what's long been a staple of science fiction, an orbiting junkyard of cast-off space debris. So where do we go from here? Forces of nature and natural collisions will continue to shape our universe. Man-made collisions? Perhaps those we can do something about. What exactly is out there? Space Junk 3D, coming soon.
Well, this, I mean, it seems like sort of a funny issue, but orbital debris is actually a major concern, and increasingly so. If you've been paying attention over the last 6 months, there have been 3 very large satellites, one of which was about the size of a school bus, that ended up re-entering the atmosphere in an uncontrolled fashion. So first of all, we're worried about where are these things going to hit on the ground. Potentially, certainly if it came down in the middle of Denver, we would probably, somebody would be having a very bad day. But an even more common problem is that there's so much debris in orbit that we're getting increasing numbers of collisions with operating spacecraft. There have been several communications, low Earth orbit communication satellites that we think have failed because of being hit by a piece of space junk. Every few months, the International Space Station has to do a divert maneuver because the tracking, ground tracking indicates that something is going to pass within a kilometer or so of them, so they raise the orbit or lower the orbit. So it really is a problem. And this movie gives a really good overview of it. So on the 13th of July, we're having the local premiere of this movie. First of all, we'll have the movie's director and producer in to introduce the IMAX, and then following the movie, we'll have a panel discussion with Dr. Don Kessler, who for, I think about 15 years was the head of NASA's Orbital Debris program, and he's featured prominently in the movie. We'll have the president of the Secure World Foundation, which is worried about the international implications of how different countries, the spacefaring nations, could actually contribute to controlling this problem. And then we'll have a local expert from the University of Colorado who's interested in how you might take care of the problem, ways that we could actually clear the debris out of Earth orbit. And so this will be a by reservation event, so if you're interested in attending, and I hope you are, you can come to the usual place on our webpage to sign up for reservations for that evening, and so hopefully we'll see lots of you that evening. And then on August 5th, of course, is the landing of the Mars Science Laboratory and the Curiosity rover. And Don had mentioned that they've refined the landing site, and this has just happened in about the last month. They did a mid-course correction on its way to Mars, and this is the Gale Crater, the target for Curiosity. The previous landing target was about 12 miles by 15 miles, and they've refined that to about 10 miles by 4 miles wide. And they've also moved the center of the landing target much closer to the base of this mountain that is their scientific target. This is just probably a better way to see this. So this was the original landing ellipse, and here's the new one as it's targeted now, and then this is the path that they hope to be able to follow, climbing up at least the lower parts of Mount Sharp. And so we're going to be doing a huge event here on the evening of August 5th to observe the landing of Curiosity. We'll be starting at about 8 p.m. and have a number of local experts, some folks from Lockheed Martin who built the entry capsule for the spacecraft, a representative from United Launch Alliance that provided the rocket, a representative from Sierra Nevada Corporation that built the winch that's going to lower the spacecraft down to the surface, and then we've got several scientists that are either currently involved or involved in previous Mars missions to tell you what it's like once a rover gets on the surface, that you're living on Mars time. You're not living on Earth time anymore. You have to operate when the rover is able to operate, and also what motivates the scientists to be part of a mission like this. So again, this is a reserved event, and we've already got, I believe, pushing 200 people signed up. We're going to have a capacity of about 1,500 for the evening, but I'd really encourage you to reserve soon. We'll be spread across the museum. We'll have speakers in IMAX. We'll have speakers here in Ricketson, in the planetarium, in Space Odyssey, and then in one of the atriums is our overflow. And so the seating assignments will be in order of when you make your reservations. So first come will be IMAX, second will be here, and then spreading throughout the rest of the museum. So as they say in Chicago, vote early and vote often. We're going to have closed circuit high-def TV. So we'll be able to take questions and answers across the museum. So we'll have speakers in IMAX, and here in Ricketson, the other 3 parts of the venues will be observing but able to ask questions. But if you would like to actually see the speakers in person, then reserve early so you can be in one of the first 2 venues. So that's, we're furiously planning that evening. There will be refreshments. We'll have some breaks built in. So we're starting at 8 p.m. The landing itself is at 11:31 p.m. Mountain Time. And the latest word we've had is that if pictures are going to come back right after landing, they will be returned within a couple minutes of landing. If they don't get those back in that time period, then it's going to be the following morning before images would come in. And so our original plan was we were going to hang out till probably 3 a.m. to see the first images coming in. And this makes it a little bit of an earlier evening. We'll probably be ending somewhere between 12:30 and 1 a.m. But if you've ever been to one of these in the past, it's sort of a big party with lots of space geeks like everyone in this room probably is. And we just have a lot of fun looking over the shoulders of the people in mission control and NASA to see this as it's happening. So I'd hope to see you on August 5th. And just to remind you, our next 60 Minutes will be on July 25th, and I expect that's going to have a whole lot more to say about MSL, because we'll be just about 10 days out, or a little less than 2 weeks out from landing at that point. So that'll be our last chance to update you before landing night. So thanks a lot, and I think at this point I'll ask Don to come back up, and he can field some questions. I guess if anybody has questions about these events at the end of when you're done with Don, then I'll take those other questions. So thanks.
Great, thanks, Steve. Sure.
You mentioned there's some little pockets of magnetosphere on Mars still.
Right. They're called crustal. It's called crustal magnetic field.
Those being targeted as eventual places for human habitation.
Well, they're pretty weak. It is a nice thought that we might be able to, seek shelter in them, but they're actually not very strong. It's more interesting, I think it's most interesting from a scientific point of view. It may give us some insight into what happened to the magnetic field when Mars did lose its magnetic field. We think it's a remnant leftover magnetic field from when Mars was a much younger planet. But it's not a strong enough magnetic field to really seek, to really find as a place to survive.
In the simplest sense, the instrument is counting, is what it's doing. So the more particles it counts within a certain frame of time, the more danger posed by radiation. The fewer, the less the danger. Is that pretty much what it comes down to?
Well, it counts, but it also counts the particle type, whether it's a proton or an iron or a neutron, something like that. And it also measures the energy of the particle. So a more massive particle with a lot of energy does more damage to an astronaut than a proton with not very much energy. So it is basically as a counter, but it counts the whole series of different particle types, and the more of that, and so when you add it up to total dose, which is what is the measure of radiation that does damage, that we use to determine how much damage we've done. It depends upon the particle types and their energies. So there's a formula which you add that all up to get your total dose. But basically it is a counter.
So any surprise with what you've seen so far in terms of?
Well, we're still working with the data, still analyzing it. We also have a lot of shielding. We're trying to, the CAD model that has the Rover design has 70,000 parts to it or something like this. So the CAD model is a very complex CAD model. We're just now getting our arms around what the shielding levels are. But I think it will provide some insight into how much shielding we are going to need.
Yes. In your little movie, you always showed the charged particles coming in from like the correct direction, but you had the uncharged particles coming in from the sides.
Right.
Why was that?
Pretty smart. No, good question. That was really just to illustrate how the instrument works. That so for the neutron channel, for example, that anti-coincidence shield goes all the way around those two detectors in the middle. So you could have a charged particle come from any direction and it'll get vetoed out. Similarly, you can have the neutral particle coming from any direction, and you can measure it. On the charged particle channel, there's that view cone, and that's about a 65-degree view cone. And the reason we need to do that is we take the energy deposited in each one of those detectors and plot them as a function of which detector it goes through. And that's the way that we use to identify what particle type it is that actually what kind of a particle actually went through the detectors. And that only works if you assume it's close to a straight line. If they go at all these different angles, you can't really analyze those data. So we know we're not collecting all the data from particles coming in from these other sides, but we kind of know the distribution of this charged particle radiation. So we just restrict it to that 65-degree view cone. But that's a really good question. Right. No, another good question. So the Martian atmosphere is roughly 6 grams per centimeter squared of equivalent shielding, but it's a complex. It's thick. It's got different. It's got a composition. It's mostly carbon dioxide, but other elements as well. So one of the our model of that atmosphere is one of the things we're testing. Also, that atmosphere varies with the temperature, with the humidity. With just the solar, with the day-night cycle. So the thickness of that atmosphere also varies. The shielding that we believe we have inside the spacecraft is on the order of, we believe, 35 to 50 grams per centimeter squared. So it's much thicker than the atmosphere will be. The shielding, just as a reference, inside an airplane is on the order of maybe 100 grams per centimeter squared of shielding. So if you're on an airplane going over the poles, you'd have maybe twice the shielding that we have inside that spacecraft. The real question is that enough shielding for an astronaut on their way to Mars, or do we really need to have more shielding like an airline would have when you're, to sufficiently protect the astronauts? Right, no, good question. And it would be kind of embarrassing for a radiation instrument to die from the radiation. Although it's happened. Having said that. So we had very, very strict requirements on having radiation-hard components. But our energy source on the rover also produces radiation. So the whole rover is living in this field of radiation. And it's very important that we use the hardest components from a radiation point of view as we can. We hope, to operate RAD for a whole solar cycle for 10 or 11 years. The nominal mission is 2 years, 2 Earth years, which is 1 Mars year. But the environment does change as a function of the solar cycle. We'd really like to operate it for 11 years. And we believe we can survive that long. There's been a couple of papers maybe where people have taken the radiation environment now that we currently model. We'll measure it and we'll verify what that really is. But if making an assumption of what the radiation environment now is, looking at the solar activity and projecting back, say 3 billion years, you could make a speculation on what that environment might be like. And there are a couple of papers that are doing that. In fact, we just hired a postdoc about 3 weeks ago that did that for his thesis work. So it's a really interesting question. The Earth being 4 billion years, Mars being 4 billion years, 3 billion is probably the time frame that you'd want to be thinking about. Yep.
Oh, you mentioned humidity affecting different changes there. When you say humidity on Mars, that's not the same.
Well, there is humidity on it. Actually, there is humidity on Mars. So. There is water vapor in the atmosphere, yeah, absolutely. And so we don't really have a weather station. We haven't had a weather station like we will have on Curiosity. to make those measurements, to have made those measurements in the past. But there are measurements of changes of the humidity and the thickness. It could vary by 10 to 20%. Right.
How does the capability of that compare to the ones on the Viking?
Oh, it's much more sophisticated. And I don't.
Ambiguous. I mean, how would you sort out?
Right.
Get beyond the example?
No, really good question. Unfortunately, I'm not a chemist, but it's a really complex organic chemistry question. The Viking instruments were quite interesting, and I think reanalyzing those data is something that scientists are doing now because it's worth revisiting that. But Sam has a whole suite of instruments, and I didn't have time or actually the skill to be able to talk about that intelligently, and then the chemists in the audience would start to question me, and I wouldn't be able to answer that. But it is actually a very sophisticated analytic lab, rivaling actually the sophistication of some of the chemistry or analytic labs on the Earth here. So it ought to be able to make much more clear distinctions than Viking. So it'll be very interesting to see the results.
What happens when the cable drops and the rover lands and the rocket portions?
Somewhere else. We hope somewhere else. It actually, so that it was a little bit, even in that movie, that was only a 5-minute movie. So, 7 minutes is still a little bit longer. It's still not quite as, it's still pretty scary, but it's still not quite as scary as it shows in the 2 minutes of the animation there. But the tether comes down sort of as it's still descending. It doesn't actually hover and then the tether comes down. It's actually, the tether comes down as it's descending. So it just comes down faster like this. And then when it detects that it's touched the ground, it just goes off. And I don't know the number, but hundreds of meters, a couple of kilometers, I don't know that answer. But the right answer is far enough away that it doesn't cause trouble for us. It crashes. So we have a lot of space junk on Mars. Well, not so different. And to put this in perspective, we did this in 1969. Apollo 11 used jets to land on the moon, and that had no atmosphere. So it had to slow from orbital velocity down to 0 on the surface of the moon. So what's different with MSL is, first of all, it's unmanned, so we have to be completely automated, although the computers they had on Apollo were not as good as your iPhone. But you have to, we're going to land completely autonomously. And then the tether's different, because on the moon you could have your descent stage on top of you, and you actually use that to boost back out into orbit. But if the descent stage landed on top of MSL, we wouldn't be able to get out from under it. So the tether is different so that we can get rid of the descent stage. But the other elements of it, and I guess the parachute's a little bit different. But the jet part is we've done in '69. We'll have to use that for humans. The reason we're doing this is it's too heavy for an airbag. The Mir landed with airbags. The Curiosity is now too big. It would pop the airbags. And a lander with humans would also have to land with jets minus the tether.
Going back to the radiation thing.
Right.
For the uncharged particles you showed too, does it matter which section they go in, or do they have to go in?
Man, you guys have got good questions. No, that's another really good point. So those two different kinds of detectors, they're different kinds of scintillators. One is a crystal called cesium iodide, and the other one is a plastic scintillator, a man-made scintillator. And they both have different sensitivities to those two different particle types, to the gamma rays and the neutrons. So one is more sensitive to neutrons, the other one's more sensitive to gamma rays. For any given particle, they're going to probably only hit one of those two detectors. But over time, you build up the statistics, and you can invert, which is fancy way of saying you take the data and you process it to figure out which particle types were which, hitting each different type of detector. So they have different sensitivities to the kind of particle as well as to the energy of the particle. And so we actually have to have both of those two kinds of detectors to distinguish between those two different kinds of particles. But that's a really good question. You want to come work for us? All right, good. Anyone else?
On that landing sequence, it sounds like, there's that magic 14 minutes, and the thing hopefully successfully touches down.
Right.
You gotta wait 14 minutes. What is the event that will tell you if it made it? Wait a while for a signal, or is it gonna be instantaneous?
It'll be a radio signal back. It'll be a bleep of a radio signal saying,
But right away, it'll touch down and it'll send something back.
It's going to be it's actually sending data the whole way down. Not the whole way down, but there's times in the descent that it'll be sending data. So the thing is that by the time it starts its descent, and by the time it lands on the surface, we still won't have the data back from the beginning of the descent. It'll already be on the surface by the time we get it. What's interesting is, Adam Stetzler said right in the beginning, that it sounds crazy, but when you go through it step by step, it's the way it had to be. It's the way it has to be from an engineering point of view. And they've done a phenomenal job. These guys are my heroes, because and when you talk to them, they're actually really confident in this system. They actually believe, when you put it at what's the likelihood that we're going to be successful in this, and they say it's at least 80%, 80 to 90%. So, they feel very comfortable about it. August 5th, hopefully you guys will all be here to hear it and to watch it on closed circuit TV. I'm going to be out at JPL, but we're hoping they're right, and we'll have a very successful landing, because it's going to be a very exciting mission on the surface. I think there will be. I don't know if the news networks will carry it, but I'm sure that there's NASA TV if you have cable or satellite. I'm not sure what the channel is for each of those, but I know that it's carried on both of those. And I know it'll be broadcast on NASA TV, and it might be on some of the public television. Steve might have an answer for that.
We will also be webcasting our event. The details are still being worked out.
So you certainly ought to be able to do it. You have one more?
It's a whole lot more fun to be here.
Go ahead.
For that last landing stage when it gets off,
Right.
does it have enough fuel to go out of Martian atmosphere so that it goes in orbit?
No. It has just enough to, it probably is right close to the end right when it lands anyway. We just want to get it out of the way so it doesn't land on top of us. And there is a lot of space junk on Mars, but, depending upon what happens, there's weathering on Earth. There's not so much weathering on Mars. So, when aliens come to explore our civilization in, in a million years, they'll find our stuff on Mars, and that'll be the evidence of human civilization. Will be our space junk on Mars. So, any other questions?
Is it going to be pretty difficult to operate this rover and the other one at the same time?
Well, we have quite a number of satellites in orbit around Mars, which we're using as relay satellites. And once we actually land, some of those satellites will have already had their primary science mission, and they're going to be used primarily as relay stations for MSL. It's all a juggling act, and we need to, so telemetry is the other one of the three resources I said, which are highly constrained. I guess volume is a fourth, but managing the telemetry is certainly an issue. Anyone else? Well, you guys had great questions. Thanks for coming. Thanks for coming tonight.
Let me just throw in a couple things. Don mentioned the orbiting spacecraft, and there was the question about the signals coming back from Curiosity. All three of the orbiters will be within sight of Curiosity when it's landing. And I think Mars Odyssey is the primary relay, but Curiosity will send out, they call it semaphores, of when a particular event happens, like it hits 3 Gs of deceleration in the atmosphere, it sends out a tone. When the parachute pops, it sends out a different tone. And so they get these very simple signals back that say this event just happened. And so they really have a very good idea of the progress of the mission. And one of the exciting things, if you remember the Phoenix landing in, 2008, the Mars Reconnaissance Orbiter was overhead, and using its high-resolution camera, the HiRISE instrument, it actually caught an image of Phoenix hanging under its parachute. They're going to try to do the same thing with Curiosity. There's no guarantees, because obviously they have to be pointed at exactly the right time, the right place at the right time. And that instrument works like a scanner, so it has to sweep across the surface. So we'll see if that happens, but we should have good indications of what's happening as soon as the radio signals get back. So I think that's it. And does anybody have any questions about the 2 events coming up that I can try and answer? Yes? The landing is a paid event. I think it's, for adults, it's $8 for members, $10 for non-members, and $5 for children. And that includes some refreshments. But all the details are on the web page. And the IMAX event is similarly priced, I believe. Okay, well, thanks for being here tonight. And thank you, Don, for joining us. And we'll see you again next month.